Hello Internet, my name is Quinn and this is Blondihacks. This is Mill Skills, a series of quick videos on learning to use your vertical mill. This is episode 7, adding features to your part. Let's go. Here's the little sample part that we're going to make. It's got some nice little features that'll let me show you a couple of different techniques. So it's got a little shelf on one end, 2 holes down the middle, and it's 2 inches long, 1 inch wide, and ½ inch thick. Here's a drawing of that same part. Now this was done in Fusion 360, but you don't have to go that fancy. It might be just in your head, or it might be written down on some scrap paper, or, you know, in one case it was written in blood on a cocktail napkin, and I'm not proud of that, but any port in a storm when inspiration strikes. This is not a proper engineering drawing, or print as they're often called. You know, there's no tolerances on anything, and there's lots of other little details missing, but this is a perfectly fine hobbyist drawing. But what I want to point out is that all of the dimensions and distances are measured from a single corner, and that's an important detail that we're going to explore here in a moment. Now I've already done the first step for any part, which is to square up your stock and bring it down to the dimensions of the outermost features on our part. You can check back on the earlier video in this series, Squaring Up Stock, to see this process. I'm not going to take you through it again. But now we need to locate our features on the part. So we've got that little shelf that we want to make, and we've got a couple of holes. Now, as you saw in the previous video in this series, we could just glue it up and scribe the line and make some measurements and punch our holes and put it over on the mill and, you know, mill it up to the line and then line up the drills on our punch marks and drill it. And that might be fine. That's going to get you within, you know, 5/1000ths on all of your dimensions and locations. But most of the time in the machine shop, we need to do better than that. And so now we need to use the power of the mill to locate features for us. Of course, machine tools don't just make cuts, they also allow us to measure distance very precisely, and so that's how we're going to locate the features on our part. Now there's 2 main ways that you're going to do this. The first, of course, is the hand wheels. The hand wheels have markings on them, and just like on the lathe, we can zero this guy at any point, and now if we move 50 thou, we know that the cutter has moved 50 thousandths. So if we know where the edge of our part is, we can move in 50 thou and place a part at 50 thousandths from the edge. And of course, just like the lathe, we have to manage backlash, because if I now try and go back, I just moved it 20 thousandths and the cutter didn't move, because that's all backlash right there. So just like on the lathe, you got to manage your backlash on the mill, and that means don't ever change direction once you've set that 0. If you do change direction, you got to come back until you're out of the backlash and then come back in again and make sure that you're not in that backlash zone when you start taking your measurements. And of course, the other method of measuring distances on machine tools is a digital readout, or DRO, as the cool kids call it. I've said previously on this channel that a DRO on the lathe for the hobbyist is kind of a luxury. Really, it's debatable how much value it adds. The mill, however, the value proposition for a DRO is absolutely clear. These things nowadays, they only cost a couple $100 for these cheap Chinese ones. They work very well, and the quality of life improvement is orders of magnitude more than the $200 that you're going to spend on this guy. So definitely get a DRO if you're going to get a mill. However, I am going to show you both the old school manual way and the DRO way of doing this, just so that you have both options. But real quick, what makes the DRO so great? Well, aside from having all the blinking lights, and who doesn't like blinking lights, the main thing that they do for you is they eliminate backlash. Fundamentally, hand wheel markings are a proxy for table movement. We're inferring how much the table is moving by how much the lead screw is turning. And because of that, indirect effectively reading, we're always going to be subject to backlash and other mechanical difficulties in the system. DROs, on the other hand, measure the travel of the table directly with something like this guy here. This is a glass scale, which is typically how they work. So there's one on the x-axis and one down here on the y. The actual scale is underneath these aluminum chip covers. But by measuring the table travel directly rather than inferring it from the rotation of a lead screw, we eliminate all of the mechanical unknowns. And then by using a glass optical scale rather than some sort of mechanical mechanism, we get much higher precision. So the real joy of the DRO is that you can just forget backlash ever existed and look at the numbers on your blinking lights and know that they will always be right. And of course, the DRO is much more precise because of those optical scales, so we can measure all the way down into the 10 thousandths and 100 thousandths of an inch quite easily. compared to our humble hand wheel here, where on this particular machine these ticks are 1,000th apart. So if you want to get any more precise than that, you're going to have to set up indicators and use other methods that I will show you. And of course, DROs have a whole laundry list of other features that makes them a no-brainer. You know, they can calculate bolt circles and do unit conversions and calculate curves and calculate tool offsets and track multiple positions on your part, and all sorts of other things that make them really, again, a no-brainer. Even the worst DRO you can buy these days is still actually really, really good. We're going to start by setting up our stock here in the vise, just like we would for any other operation. And we've already squared it up, so we should have no trouble getting this guy nice and seated in there. And of course, tappy tap, tap it in. Parallels are snug, we're good to go. So we're going to start by making this little shelf here that was marked on our drawing. And well, here comes the catch. We know that that shelf is 250 thou deep in both dimensions from the edges of our part. But wait a minute, we've got this cutter here that could be anywhere in space, and all those methods of measuring distance that we looked at are all relative. There's no zero here, so we need to find a zero. Now, as I said earlier, it's always good practice to pick one corner of your part in 3D space and make that your origin and measure all features from that zero. So what we really want to be able to do is get the bottom corner of our cutter that's going to be removing the material onto our origin. We want to get that point right there to 0, and then from there we can use our DRO and our hand wheels and whatever to measure the travel of that cutter in to where the edge of our feature needs to be, and then the same thing downward. Now there's a whole bunch of ways to do this, and they all have varying levels of precision, so I'm going to walk you through each one. The first and simplest method of getting our cutter on our zero is called touching off, and it's exactly what it sounds like. We just bring this cutter down with the machine running very slowly and very carefully until we just see it graze the surface of the part. You'll see a little bit of a chip form. Now, obviously, you're going to cost yourself 1 or 2 thou doing this, because if you weren't doing a cut, you wouldn't see a chip. And if you're doing a cut, you're removing material. So when using the touching off method to find a surface, your cutter is going to end up just a dog's breath inside where that surface actually is. But in many, many cases, that's close enough. Now you might be wondering, why don't you just bring the cutter down until it touches the surface while stationary? Well, that's actually less precise than doing it with the cutter spinning, because you have no feel in any of these controls. Remember, we're doing this by either lowering the quill with a fine feed, which will be a worm drive, or we're raising the knee or lowering the column with lead screws. None of those have a particularly sensitive feel, so you're not going to feel the cutter touching the surface until it's really obvious, and by then you've dug in 5 or more thousandths. But with the cutter spinning, we can visually see when a couple of chips are whisked off the surface, and so we don't have to rely on the physical feel of the controls. So I'm going to demonstrate this right now using the fine feed on my quill, but you could do this with the knee or the column or whatever's easiest on your machine. So it looked like nothing was happening for a really long time there because I was moving the quill down very, very slowly until I got just a couple of whiskers of chips here on the surface, and this is probably a 1 or a 1.5 thou cut here. Now that we know the cutter is on that top surface, we can zero out all of our vertical measuring systems that we have. So if we're going to be tracking our depth of cut with the quill, which is pretty common, then I can just go ahead and zero out the DRO on the quill. If you don't have a quill DRO, if you're using all hand wheels for this, then you got to zero out your vertical hand wheel. So alternatively, I would come up here and zero out the hand wheel on my column, like so, and now we can move downward with this hand wheel and measure distance from that surface of that part up here. Now mills have all sorts of different distance measuring setups on them, so you may not have a DRO on your quill and you may not have quill markings that can measure distance, and maybe you don't want to use your column or your knee for measuring, but maybe you do have a DRO, and if you've got a DRO on your Z-axis, then of course now we can just zero that guy out, and now we can measure vertical travel here and know that we are again measuring precisely the depth of our feature from the top surface of our part. And the second method for finding the surface, which is a little more precise than touching off, is to use a feeler gauge or a piece of precision shim stock like I have here, and just slide that guy in there and then feed downwards, and you can feel on that shim stock when the cutter is touching the surface. And just like any feeler gauge operation, you don't want to pinch it, but you want to just kind of feel the drag on it. So right there, I've got light drag on my feeler. So I pull that guy out, and I know this is an 1/8 thou shim, so I just move the cutter down 1/8 thou from here using the various distance measuring methods that we've looked at. Up here on the quill DRO, it's reading -9 thousandths, and remember this was zeroed with the touch-off method, and so you can see that with our 1/8 thou shim, our touch-off was actually a 1 thou cut. So if I move this down 8 thousandths, it's going to be registering -1, and this is going to be a more precise indication of where the top of that part is. So if I zero this guy out again, I'll be able to sweep the cutter over the top without actually taking a 1 thou cut. Here's another similar method that a lot of people like. I don't personally use this one. I'm not a big fan of getting my hand in here like this, but I'll show it to you for completeness. So the trick here is you take a piece of standard printer or copier paper, which is generally accepted to be 4 thousandths thick, and we slide it under the cutter with the cutter running, and then we downfeed very carefully until the cutter grabs the paper and pulls it out of our fingers. And then we know the cutter is exactly 4 thou above the surface, and we can dial down that 4 thou, and we're on the surface. And as you can see, we're at -3.5 thousandths here. So again, this was zeroed with the shim method. So this is basically the thickness of that paper, within 0.5 thousandths. So the paper method is also quite precise. But as I said, I'm not a huge fan of it because it does require getting your cat treats closer to the murder machine than I like to do. Now, all those backwoods methods for finding our zero are fine, but is there a better way? Yes, there is. Edge finding. This is an edge finder. Sometimes they have a point on the other side, sometimes they don't. We're not going to worry about that. This is for a different purpose. What we're interested in is this end here. This is a precision ground arbor with this precision ground shaft at the end, and this shaft can move in one plane, and it is spring-loaded. And this very clever little device will let us find the edge of that part very precisely without any cutting or shimming or meat grinding. All we do with this guy is mount it like you would a cutter, turn the machine on, about 1,000 RPM is usually what these guys want, and then we bring it down beside our part, and this guy's going to be flopping all over because the spindle is running, and then what's going to happen is, as you bring it over very slowly, you're going to see this guy true itself up, and then you keep going a little bit past that point, and then you're going to see this guy kick itself over. Now what's happening is, there's a very precision ground surface on the shaft here, and then we've got a machined surface there, two precision surfaces, and well, two surfaces can't coexist in the same space, so when this surface is trying to occupy the same space as that surface, it's forced to kick over, and that's how we know the edge of the edge finder is on the edge of our part. Now the other effect here is because it's spinning, this guy kind of wants to roll on the surface, so as soon as it gets enough traction, as soon as it's contacting that surface well enough that it can get a little bit of grip, it's going to kind of want to roll off to the side as well. So that's going to tell us exactly where that edge is in this plane, in the y-axis of the mill. And then you would do the same thing on this axis. You bring the edge finder around and do the same thing on this side, and that'll tell us where this plane is. Now we call these guys edge finders. They're technically point finders. It's finding a single point on the corner of this part here. But because this is a machined surface, we know that all points on this top edge here are along the y-axis of the mill, so it's effectively finding the edge because that surface is machined. But because of that effect, you can't edge find on a saw-cut surface very effectively or on a surface that's at an angle. None of that's really going to work very well because, again, you're not then going to be finding the edge, you're going to be finding some arbitrary point on that line that you're testing. The moment you see that kick over, stop cranking because you found the edge. Now you need to crank up slowly because it's very easy to go too far. And again, because this guy is spring-loaded, you can easily crank past the moment where it just kicked over. So you want to crank in nice and slowly. If you're a little bit too aggressive with your cranking, then you're going to overshoot that moment where the two surfaces are just occupying the same space. Now we were finding a y edge, so what we've actually found is the x coordinate of our origin. So now we can zero the x on our DRO or our hand wheel. And then we can go ahead and find the long edge of our part, and that will allow us to zero our Y hand wheel or Y on the DRO. And then we will have all 3 zeros for our origin of our part in 3D space. Now wait a minute, I pulled a fast one on you there, didn't I? We switched from finding the top surface with the Backwoods methods to finding the sides with the fancy edge finder. And well, that's because there really isn't a tool like an edge finder for finding the top surface of the part. So generally you're going to definitely be using one of those other methods for finding the top surface. I'm again partial to the shim method, but you want to understand the precision of your part. A lot of times there will be a dimension on the feature that is less critical. So if the depth of our little shelf, for example, is less critical, if we can accept a 1 or 2 thou error in that depth, then we can use the touch-off method for the top and an edge finder for the side, for example. You always want to be thinking about that trade-off of precision and time, because, for example, the touch-off method is much faster than setting up an edge finder. You might have to change your collet, and you got to move the head and the quill to get the little thing lined up, and it's way more setup time to use an edge finder than to just touch off. So if you can accept a couple thou of error in a dimension for a feature, then just touching off on the side and touching off on the top might be a much more efficient way to get your feature made. There are also electronic surface detectors, as typically used in CNC machines, where they use capacitance or some other method to electronically detect when the surface is exactly touching an electronic probe. And you know, those are great. They're expensive, a little bit out of the reach for the hobby shop. So learn to touch off, use the shims, use your edge finders, and so on. We're not done with our friend the edge finder yet. We found those 2 edges and we zeroed this guy out. So let's go ahead and move to those zeros. So now we're right on the origin of our part, right? Wrong. What we actually know is this corner is right on this surface. But that's not a very useful reference. What we actually want is the center axis of the spindle to be exactly on our point right there. So that's where the final trick of the edge finder comes in, which is that this little shaft here that we used to find the edges is extremely precision ground to an exact known dimension. So when you buy an edge finder, it'll tell you what the diameter of this shaft is, and so we can just offset by that amount to get the center axis of the spindle right over our corner. This happens to be a 200 thou diameter edge finder, so 100 thou, the radius of that edge finder, is the amount that we need to move over to get our spindle axis centered. So I'm going to move the X over to 100, like so. Do the same with the Y. And now you can see how the corner of our part is in the middle of the shaft on that edge finder. So the center axis of the spindle is now on our origin, and that's what we really want. So then we come back up here and we zero this guy again, and now we're really on the origin of our part. And again, if we're going old school, then we just zero out our hand wheels on the 2 axes. Now if you're using the hand wheels, you want to make sure that you've taken out the backlash from this direction. In this case, my origin is here, my features are all over here to the right of the origin. I want to make sure I'm approaching the origin from the left, and that when I get to the origin, there's no backlash left on those hand wheels, so that now I can measure inward from my origin and know that the markings on the hand wheels are going to be correct. So this takes some brain power, and you got to be careful, because again, if you ever change direction and start going back, now your hand wheels are meaningless until you get out here and come back in and take out that backlash again. Those little mental gymnastics are why I think the DRO is really a kind of a no-brainer on the mill. But know that you can get by and use the hand wheels. People did it that way for 100 years and it was fine. So don't panic if you only have hand wheels, but start saving up for that DRO. We want to make that little shelf. So we got to do a little more math. Machinists are good at math, and this is why. What we really care about is that the edge of this cutter, the area that's removing material, is on the line where the edge of that feature needs to be. So we want to be in 250 thou from here and 250 thou down, and we want this corner to end up on the bottom corner of that shelf on the final pass. So how do we do that? Well, you got to take the diameter of your cutter. Now we're making a 250 thou wide feature, but because it's a shelf on the edge of the part, you can use any size cutter you want, really. It doesn't have to be a 1/4 inch cutter. So I've got a 1/2 inch cutter here, 500 thou. So what we do is, if it's a 500 thou cutter and these are precision made, then you know that the radius of this cutter is 250 thou. So in our case, this is easy. If I put this cutter in here, when the center axis of this cutter is at 0, then I know that the outer edge of this cutter is 250 thou in, which is what we want. But if I was going to cut that same feature with this 1-inch cutter, now we got to do a little more math, because now if I put this cutter in here as is at 0, the center line of the cutter is going to be on 0, and the outer edge of our cutter is going to be 500 thou in, because the radius of this cutter is 500 thou. And that's obviously way too deep for our feature. So an easy way to do this math for any size cutter is to imagine your 0, subtract the radius of your cutter, 500 thou in this case, and then add the size of the feature that you want. So if we go negative 500 plus 250, we end up with negative 250. So we go to negative 250 using our DRO or the hand wheels, and then the edge of this cutter will be 250 in from the edge where we want our feature to be. Comes in women's and men's and lots of cool colors. Blondihacks.com/store. All right, so we've got everything zeroed out on our origin, and we know how to find the edge of the cutter and match that up to where we want the edge of our feature to be. But we still have to pick a milling strategy for our feature. Now, what do I mean by milling strategy? Well, we have to control our depth of cut, because while it would be nice to just make every feature in one pass, you usually can't do that, especially on these hobby mills. So if you're cutting steel, for example, you might be limited to 30 or 40 thousandths depth of cut. And so you have to plan out how you can create the feature of the dimensions you want using that depth of cut. Our sample part here is aluminum, but I still don't want to take, crazy depths of cut, and I certainly can't do a 250 thou depth of cut, 250 thou wide in a single pass on this little mill. A big Bridgeport or a Wells Index or something wouldn't blink at that, but here in the hobby shop, we got to be a little more careful. But the same logic applies if you were doing a much larger feature on a larger mill. You have to have a milling strategy. For our little shelf here, it's quite easy because it's a fairly small feature, so we can just bring the cutter over to the edge is 250 thou in, and then we can just do multiple passes working our way down until we get to the 250 depth, and Bob's your uncle. But imagine if this ledge was, say, 1 inch wide and we're using the same 1/2 inch cutter. Well, we can't really do that anymore because obviously the feature is wider than our mill, and you may not want to do full width passes on your mill depending on how rigid your machine is and various other variables. So there's a couple of approaches you might do. You might go, say, down 50 thou and then do multiple passes over until you get to the edge of your feature, or you might mill all the way down to your final depth and then side mill your way across until you get to the final width of your feature. So there's different ways to do it. It's a fairly in-depth topic to recommend one method or another. It depends on the cutter you're using, the material, the size of the feature, how rigid your machine is, and many other variables. So you'll just have to experiment with that for now, but just make sure that whatever you're doing, you're not exceeding the depths of cut that your machine can handle in this material. But again, for our little feature, it's easy because we can just bring the edge of that cutter in 250 thou using the methods that we discussed. And then we know that the edge of that feature will be in the right place. Now we're going to be milling on the y-axis of the machine. Remember that the cutter spins this way. So we're going to be milling back to front so that this is a conventional cut and not a climb cut. You can refer to my earlier video in this series on conventional milling versus climb milling. You want to be thinking about that, of course. So I'm going to be winding this guy back here clear of the part behind it, and then I'm going to dial in my depth of cut. So let's do a 30 thou pass, just nice and gentle to start with. And then I lock the quill and the column, and this is aluminum, so I'm using WD-40 as a cutting fluid. This is a 1/2 inch cutter in aluminum, so my RPM is going to be 1200. You can see the feeds and speeds video for how I arrive at that number, but short version is that aluminum loves speed. All right, let's keep calm and make chips. There's our first pass. Just get some of those chips off of there so we can see what we're doing. Looks like the cutter is cutting well. We're happy with that. So now I'm just going to repeat that process. And as you go down, you can try deeper and deeper cuts and just see how the machine responds, how the material responds, and build up your experience with depth of cut calculations that way. Okay, I've left 20 thou there for a finishing pass, so now it's time to talk about hitting those dimensions. So we're going to bring this guy out, and then we're going to clean this guy up, and we're going to deburr it so that we can take our measurements. You can check out my video on deburring for why this matters, but the short answer is that we don't want to measure the burrs in our calculations. So we've got 228.5 there, so we've got 21.5 thousandths to come out of there for our finishing pass. Now I pulled another fast one on you. We're milling down and we're checking our measurements as we go and being all careful about that. But we didn't actually do that for this dimension. We just moved the cutter into position and assumed that this distance here would end up at 250 thou. So what I've done is sort of the quick and dirty trust the DRO method this way, and the meticulous check our measurements as we go and sneak up on it method this way. And both of those methods can be perfectly valid, depends on the tolerances of the two dimensions. So if one of these dimensions is really critical and the other one is not, then you might be, a little more trusting of the DRO in that particular dimension. But if you trust the DRO, there are going to be chances for errors to creep in. It's going to depend on how precise your edge finding was and various other factors. So if both of these dimensions were critical, what we would want to do is on our first pass, rather than going in the full 250 according to the DRO or the hand wheels, we would want to maybe do a couple of passes working our way across at the same depth of cut until we get to the exact right dimension this way, and then mill our way down. And then we really know these two dimensions are both going to be accurate. But just for giggles, let's see how we did do in that other dimension. So I'll just deburr this edge so that I can measure that dimension. And then we'll come in here with the depth micrometer and see how we did. So there you go. We're actually 1.5 thou off in that dimension. So just goes to show, if it really matters, you got to be careful and measure. Don't necessarily trust all of your instruments. Now, the other variable I haven't talked about here is surface finish. If surface finish is critical on both of these sides, that's the other reason that you wouldn't want to just do it in one pass like we're doing with the horizontal dimension here. By working full width on this feature and just working our way down, the surface finish on this vertical face is probably not going to be as good as it could be. If the cutter is loaded up, there might be very faint ridges here and so forth. So if you want absolute best surface finishes, then you want to come in not quite all the way, work your way down not quite all the way, and then do a finishing pass of, say, 10 thousandths where the cutter is exactly in the right position for the final feature on both dimensions. So you're going to machine both of these faces with a light pass at the same time, and that's going to guarantee dimension and best possible surface finish. But of course, all of that takes more time to set up and more time to think about, more chances for error. So once again, precision and quality are always a balance against time. All right, needs a little deburring, of course, but there's our little step feature. But that is all the time we have. In part 2, we're going to make those holes, and we're going to learn a few more techniques for positioning features. Thanks for watching. Check out my Patreon and the Blondihacks store, link below. See you next time.